Chapter 1, Stress, Application of Normal and Shearing Stresses in Design. Example 2. So in this example, we have a configuration of a embedded plate inside the concrete. So in this example, we have a steel plate with a thickness of a quarter of inches embedded in a concrete wall to hold a high stress cable. Mhm. Strength cable. So the diameter of the hole, there is a hole inside the plate which can have a pin inside it to connect the high strength cable for pulling part, which has a 3/4 of inch and ultimate strength of steel is 36 ksi kilopound square inches, and ultimate bonding stress between the two materials, all the bond stress between concrete and uh, steel plate is 300 pound square inches, knowing that the factor of safety for the entire system is 3.6 when pulling out force is 2.5 kilopounds. So when P is 2.5 kips, mhm, first we want to determine what is the width of A of the plate. So if this is our plate, we want to know what is the width of plate. A is what? And also in part B, we want to know what is the minimum depth required for plate that it can still be stable inside a concrete. Mhm. Let's approach the problem. So if this is for part A, and in part A we want to know what A is, and that's the width of steel plate, which is this is a steel plate inside the concrete. So in this part, P failure is equal to sigma failure, force of failure is equal to normal stress failure times a net cross sectional area, because if you have a hole inside a plate and you pull it, you have to subtract the hole from the whole area. So in that case, and we do know factor of safety is a force of failure over available force, which is here. Mhm. So Fs is sigma failure times net area, which we talk about it in a second, over available force, which is P. So if this is the pulling part, if we just magnify this part here, mm, this part, when you apply the pulling force, this is the net cross-sectional area. You have to subtract the pin area from the the width of the. So if the width of concrete steel plate is A, you have to subtract the diameter of the pin, which is provided to be 3/4 of inches. So that's A minus D, A minus D, mm, A minus D, and O times T, which is the thickness. So we're talking about this area. Mhm. So, and A net is again A minus D times the thickness. A minus D times the thickness. So if you replace it, if you solve the equation for um, factor of in and you if you reorganize the equation, that's factor of safety times pulling force. It's sigma failure times A minus D in parentheses times the thickness. So if you rearrange the equation based off A, width of the steel plate, which is A, and that gives you A is equal to a this parametric formula D plus factor of safety times P over sigma failure times the thickness of plate. And if you replace that by the numeric value, it just gives us a D is a 3/4 of inches. So that's a 3/4 plus a factor of safety for the entire system is 3.6 times pulling out force is provided to be 2.5 kilopounds over sigma failure, which is provided 36, and times the thickness, which is the thickness of plate, is 1/4 of inches. And if you do the mass, it just gives you the width of a, a steel plate is equal to 1.75 inches. In part B, so based on shear between plate and slab, shear or friction area, we for that calculation we have the two part of the shearing force or frictional force when we try to pulling out the steel plate, and one is at the top, the other is in the bottom. So that's the two part that at the frictional force apply or shear stress applies there. That's A times B and two of them. And at the same time, we do have two shearing areas at the site. So one is over here and the other one is, so these are the area, one at the top, one at the below by the area of A times B, and two at the sides by the area of B times the thickness of a steel, B times the thickness of a steel. So in that case, frictional area is A is equal to 2 times AB, the greenish area, plus 2 times BT, which is this part at the sides. And if you reorganize that, it just simplify that. That's 2B times open bracket A plus T close brackets. And that's our area. Then in this time, P failure is tau failure based off shear this time times the area of shear, and that's 2 tau failure times A plus T times in brackets times B. And at the same time, we do know the factor of safety is again P failure over available P. And if we call these two equation 1 and 2, and then 1 is equal to 2, it just gives us a Fs times P is equal to 2 times tau failure times A plus T times the B desired length. And also from the data statement, we do have tau failure is 0.3 ksi. So if you replace that in the equation, if you solve this equation for B in parametric, then replace the numeric value, it just gives you a B sufficient length is inside of a steel plate inside the concrete is equal to 7.5 inches. Thank you.